Okay, so let's talk about the second problem, which is a radioactive decay. This is a part of the nuclear chemistry problem that has a practical, one of the practical use, which is dating some rock, for example. So let's read the problems. The rock was found, and it contains this 40. Okay, so potassium 40, and then also the argon 40. So, and then also we assume that all of the argon came from the decay of potassium 40. What is the ages? What is the age of rock in years? So let's go to let's look at the periodic table that we used before. Where is potassium? So potassium has a atomic number 19, and then argon is atomic number of 18. So, because we just learned about the nuclear chemistry, I think that we can write some equation, like this, which is okay, potassium 40, which is 19, decays to argon 40, which is an 18. So that make up, I need to take one proton, but charges or mass is 0, right? So this is what we call the positron. So positron is being emitted by this process. And this is known to be what is called the first order decay. And I am going to write this equation into more simplified version of. So A goes to the product, and I would say first order kinetics. This is the one that we already discussed it before, and we talked about half-life. And you remember the half-life that you can find in the reference table in the first order kinetics. They give you a half-life, which is a T-half. Half-life is defined as, if you look at the reference sheet, the ln2 divided by decay constant K. Okay, so from here, actually you can get the most crucial one, which is a K. That is ln2 by half-life. And if you plug those numbers, the K value that you can find out is 5.30, 10 to the minus 10, and it has a unit per year, right? If you look at that, it has a unit of per year basis. And then let me give you a little pictures. So if you have a rock with a potassium 40, and they decay. So as time goes on, you'll find this, and you'll have a little bit of argon 40, and still everything is remain as potassium 40, and then as it goes, that will be, I'm just giving you as a graphical example of that. So the longer it goes, we know you will have a more moles of argon 40 being converted into. So I want to know what's the initial concentration of the potassium 40. So what I call in my notation is initial. Okay, this is a time 0. That will be the way the important clue is given here. All the argon came from decay of potassium 40, right? Potassium. So it is regardless is whether it changes or not, the number of moles of the argon and the potassium at any time is representing the initial number of moles of potassium. So therefore, my A naught here, which is an initial number of moles, is essentially summation of 0.07 10 to the minus 5 plus 1.15 10 to the minus 5 mole. Okay, so this is one is potassium, while the other is argon. That is 3.22 10 to the minus 5 mole. Okay, and then at some point, right? So we don't know the time, and this is something that we want to find out because we use a unit of a per year basis. So the number that we got will have a unit of an year. Okay, so that's the sort of the already the correlation that you will anticipate because of the k value from going back to here. There's a per year half-life was given into the year. Which is I think that I want to make sure that this value is 1.3 10 to the minus plus 9 year. Okay, so that was a half-life given in the problem for the property of potassium 40 isotope. Okay, which is 19. Okay, so I got this one then. What's my A was given in the problem was that was for the current time. This is one. Okay, that was a potassium concentration, which is a 2.07 10 to the minus 5. So then I am going to use this equation that is, you can also find this the reference table, which is ln A naught over A is a KT. And that's a one that you want to find out. But I also want you to, because I have a time to, in this video recording, this equation is essentially, you can just plug it in and get the answer. But I also want you to know, having this concept, the concentration of A, okay, the concentration of A, which is a concentration of potassium 40 at any time, is A naught, initial concentration of potassium 40, times the exponential to the minus KT. And so this is a first order kinetic decay, and that's what we call the exponential decay. So if I have a graph like this, you should have this kind of conceptual understanding in your mind. And so initial concentration is A naught here, and this y-axis is essentially concentration of A as a function of time. Okay, and then from the 0 time. And this is your initial point, and if you plot this, this should looks like that. Okay, so it's called the exponential decay, and we are the problem is asking that, okay, I give it to you, the initial one is 3.22 10 to the minus 5 mole. And they're asking you, what about what time happened when your A at any time, which is corresponding to here. This is what is the number? 2.07 10 to the minus 5 mole. And they are asking you that how long do I need to take? So this is the T that was asking for the question. So you can do this, and actually I don't have to reinvent the wheel. So this is a number, and then you can reshuffle this equation saying, okay, I only need a T, which is a 1 over K natural log concentration initial divided by concentration A. And that's the number, and you plug in all the numbers, and you will get this one, right? So that means 820 10 to the 6 years, which is 820 million years ago. This one was formed. Okay, so that's how how the isotope first order decay kinetics can be used, and I want to give you extra information to show it to you about this, the idea about exponential decay, form of a graph so that you will have, okay, this is an exponential decay, how this concentration of potassium is getting smaller and smaller, right? And then this is how you can find out. Thank you for your attention. Okay, see you next time.